Guys, so today in today's mathematics class, we're going to be discussing about a very interesting and yet lesser understood topic of mathematics, especially like amongst the students of India. Like it's really misunderstood. What most teachers do is that they just make students memorize formula and teach them when to and how to apply these formulas, and that's about it. They don't get into the depth of this topic, and their students often lack the visual understanding of this. They lack the mental you know uh, portrait of the subject. Today, that is exactly what I'm gonna be trying to provide you with. The name of the topic is infamous. It's one of the two branches of calculus, differentiation. So you guys are all familiar with this thing that let's say we take a function f of x equals x to the power n. Differentiating this f dash of x, you guys know it would be n times x to the power n minus 1. You guys know that. But you guys don't know where this came from, right? You guys also know that if f of x equals sin x, then f dash of x, would be cosine of x, or in short, cos of x. Most people try to make the students recognize this, and when I was taught this by traditional mainstream teacher, this I was taught as well, and I had absolutely no idea what is going on in like in core level. Later, I got to some new teachers, some better quality teachers who took me uh, you know, this thing but in a better way, and try to help me build get a very clear mental portrait of this topic. Let's see if I can provide you guys with that as well. So, at first, if you want to understand differentiation, you have to understand graphs. Yes, this graphs, and we are only going to be talking about two-dimensional graphs because I'm going to be talking about here is two-dimensional calculus, not three-dimensional calculus. So I'll talk about them later. Right now, we are only going to be talking about two-dimensional graphs. Let's say f of x is x square, and this axis represents increment of x, and this axis represents increment of y. And I know that, like, you guys know what like y here is, right? Y is nothing but function of x. Like, we're not gonna be plotting a graph to understand the relationship of y with x, basically this relationship of function of x with x, uh, visually, how that looks visually. In order to do that, we are gonna be taking y represents function of x, the value of function of x. So x square is y. So if we plot this graph, we'll get a graph that looks something like this. I'm only gonna be talking about the first quadrant. I know actually the graph of f of x equals x square would look something like this, where the same kind of shape would go on both sides of the x-axis, both positive and negative. But we're only going to be talking about positive side today. And honestly, if you understand one side, you probably would have a hard time understanding other side as well. So, what is differentiation? What about derivation? It's also called derivation. So, what is this? differentiation is at a fundamental level is nothing but the rate of change of a graph. Like, let's say if I had a graph of, let's say, a moving particle of which t-axis represents, so x-axis represents time and the y-axis represents displacement. Yeah, the graph looks something like this. It's a straight line. So, what would be the rate of change of this graph? What is the meaning of the rate of change? Displacement, let's say, initially at point 0, when t equals 0, displacement also equals 0, and we have a point here P and A, where the coordinates of these 2 points are, for A it's t1 comma d1, and for B is t2 comma d2. Now, what would be the rate of change of this graph? Like how fast this graph changes? Wouldn't that be, the value of, y coordinate at B minus the value of y coordinate at A divided by the value of x coordinate minus the value of x coordinate of point B and minus the x coordinate of point A. So rate of change here would be d2 minus d1 by d2 minus d1. So you guys can see, like, why, first of all, why is that? Like, initially we were at a certain displacement, and then after some time we were another displacement, and initially the time we had spent since the beginning of our journey was t1, and finally when we got to point B, the time we had spent from like when we were at the beginning of our journey is t2. So the change in displacement is nothing but d2 by d2 minus d1, and in what time did we accomplish that? Change in displacement. Wouldn't that be t2 minus t1? Of course it would. Of course. So this is why the rate of change is this thing, d2 minus d1 by d2 minus t1. So this is why for any graph the rate of change would be rate of change between 2 points would be the difference of y coordinates at the, of both points divided by the x coordinates of both points. So actually let me keep it like that. Now here in this original graph of ours, the graph is not a straight line, it's a curve. So that means the rate of change is also different. Like if let's say x is 1, so y would also be 1 because y is nothing but x square. Y is x square. So and x is, if x is 3, sorry 2, and y would be 4. If x is 3, y would be 9. If x is 4, then y would be 16. So you guys can say that the rate of at which the value of y is changing is not constant. The rate itself is changing. So how do we find a general form of the rate of change of this graph? That is where calculus comes in. That is where this sort of calculus differentiation comes in. So how do you actually calculate this? Let's say we have 2 points A and B. The coordinate of A at x coordinate, let's say, is x. So the y coordinate will be square of that, x square, and the coordinates of point B, let them be x plus h comma x plus h whole square, where h is the vertical distance between A and B. This much is h. I don't know if you guys can see that properly, so let me try it here. This much is h. So since this is h is the vertical distance between A and B, so if the x coordinate of point A is x, so the x coordinate of point B would be x plus h. Okay, so in this graph, the average, the rate of change between point B and point A, how much would that be? If you connect these two points, point A and B, wouldn't that form a line, a straight line? Because what do we know? We know that if we connect two like distinct points, then that would form a straight line. And how do we change? How do we find the rate of change of a straight line? With this formula, y2 minus y1 y x2 minus x1. Nothing fancy with that. Immediately draw a straight line here, connecting these two dots. Roughly looks like a straight line this. So, yeah. Now, the rate of change of this, what would this be? This would be y2 which in this case is x plus h whole square minus y1, that is x square, y2 x plus h minus y1, oh sorry, x1. This one is x2 and this one is x1, so minus x1. So this x and x would cancel out. Rate of change, let me write it down here. Rate of change is this. This expression would be evaluated as x square plus 2xh plus a square minus x square over h. You can also cancel out x square and x square here, and from this 2x plus h square, if we factor out h, this will be nothing but 2x plus h times h by h. H and h would cancel each other, and this would just leave us with 2x plus h. Okay, so the average rate of change between point A and point B is, as we calculate it here, 2x plus h, where h is the vertical distance between point A and point B. Okay, I don't think I don't think there should be any problem with that. This is h. Sorry for my terrible handwriting. This is h. Okay, but we don't want that. We don't want to find the average rate of change between two points. What we want to find here is what is the rate of change for a specific point, any specific point. What would it be? So, in order to find that, what we'll have to do is we'll have to take these 2 points A and B very, 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 very closely to each other. If, let me write it down here, if A and B are very close to each other, then how would this graph look like? Sorry, it's not a straight line. This is a curve. So if these 2 points were very too close to each other, and this graph look something like this. Point A is here and point B is here, B is here, A, and B. I know these two still look very far apart from each other, but what I'm trying to say is that the distance between these two points A and B is very small. Like let's say it's 10 to the power minus 10 or something like that. So that way, we would be able to say that A and B are the same points. You guys might say that how come that works? We know that A and B are not the same points. Just because the distance between them is very small doesn't mean that it doesn't exist. It exists even if that's even if it has a very small value. This is where a big law, unspoken law of advanced science comes in. And this is applied in any branch of advanced science, be it mathematics, be it physics, be it chemistry, be it biology, any branch. It's assumptions because, like, in higher levels, getting to exact calculations, exact 100% precise calculations is just not possible. So, in order to execute those calculations, we'll have to, what we have to do is we'll have to assume a few things. Otherwise, we just won't be able to get anywhere with the calculations. So, since we have assumed that the distance between A and B is very small, like 10 to the power minus 100 units, let's say, that is a very, very small distance. So, you can say that it just does not exist. The distance, we can say that it's absolute zero. So, if it is zero, then what do we be able to say that A and B are the same points? Okay, and if A and B are the same points, then H, the vertical distance between A and B, that would be just zero. Okay, if let me write it down here actually. If A and B, sorry for the word, I just writing it actually. A and B are actually let me write down this way. If A and B are very close, H would be zero. Would be H would be close to zero. You can also say that the other way around. Like if H is very small, then point A and point B would be very, 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 very close to each other. So the rate of change here would be 2x plus h. Since h is very small, you can actually ignore it and say that it's just going to be 2x. Okay, this is the formula where this is the primary formula of calculus when the function we have is a polynomial function. So the derivatives, which is the rate of change of a function x square, f of x equals x square, is nothing but 2 times x. Now, calm down a bit. I know you guys might have a lot of doubts in your mind. Let them boil for a moment. This way, we would be able to, uh, conclude a lot of stuff. We found out that the rate of change of x square is 2x, and if you calculate yourself, you'll find out the rate of change of x to the power x to the 3 would be 3x square. X to the fourth would be 4x cube. And this will just continue this like that. And if you take further derivatives of this would be 4 times 3 times x square, like that. This is how it would work. So if we try to find a general formula of derivatives of polynomial functions, how would they look like? How would it look like? If f of x equals x to the power n, if n had been 2, then derivative of f of x, f dash x, it would have been 2 of 2 times x. If n was equal to 3, then it would be 3 times x to the x to x square. So let's say that, because you can see a pattern when I talk about derivatives. Uh, First, we are having to multiply our variable x with the power that it originally had. So that would be n times x, and then we will have to subtract 1 from the power of x. Uh, Derivatives of x to the power x 2 x square is 2x. So the power of x at that moment was uh, the original power 2 minus 1, that is just 1. So we can write it down as n times x to the power n minus 1. This is the general formula of polynomial functions, the derivatives of those. Now, let's say if we have a function that is not a polynomial, how would that look like? Let's say you have function fx. F dash of x, how would look like that? Period of change is nothing but the difference of y coordinates divided by the difference of x coordinates. So from our previous calculations, actually I made a mistake. No, I picked that out. You can rewind the video and check it out. It would be function of x plus h minus function of x by h. But there is a twist. We know this formula only works when we take h equals very small. Only that way point A and point B would be, these two points would be very close to each other, and the formula that we have calculated out of our assumptions around the stuff would make sense. All of that would only work if h is very small. It's so small that at certain points you can just take h as 0. So how do we represent the fact that h is very small here? We do that with limits. I am not gonna get into very depth of the topic limits. Just remember that I have written. First of all, this is pronounced as limit of h tends to 0, or you can say it like limit. It is not. Actually, I've said this another way, like as h approaches 0, function of fx, sorry, f of f plus f of x plus h minus f of x by h. You can say it like that. And what does this limit say? That it's saying that the value of x here is very small. It's very close to 0, but it's not exactly 0. It can be slightly larger than 0. It can be slightly smaller than 0. Like let's say it can 10 to the power minus 20, or it can be minus 10 to the power minus 20. Both way, first example was bigger than 0, and second example was smaller than 0. But both are very close to each other. And this limit is just telling us that the value of x tends to 0. Like we cannot plug in 0 for h, because if we do that, this whole thing will be divided by 0, and dividing anything by 0 is not defining mathematics. It's infinity, and infinity is not defining mathematics. But this is the general formula of any function. If we want to find out the difference, derivatives of what any function looks like, you can use this general formula. Limit of h tends to 0 of f of x plus h minus f of x by h. So I think this should have cleared out a lot of doubts in your mind. I know still a lot of stuff remain, like non-polynomial functions like trigonometric functions or exponential functions or logarithmic functions. How would these functions be derived? In next video, we're going to be discussing about exactly that. Before that, if you have any doubts regarding this video, then definitely let me know in the comments about that, and I'll try to provide you with answers of that. Okay, so bye guys. See you tomorrow.